Alright, so now let's take a look at how to find the capacitance for a cylindrical capacitor. So if I were to draw a cylindrical capacitor, let's do a cross section here. Might look something like that with, oops, let's do it a little bigger than that. Alright, we have an inside plate, if you will, of radius A and an outside plate of radius B. Right? Let's say that these two plates, or these two cylindrical plates, if you will, are fully charged such that the inside is of charge Q and the outside is of charge minus Q. That creates an electric field going from the inside out. Right, something like that. And, whoops, electric field. And so we want to find the expression for the capacitance of this configuration, right? Remember, capacitance is C equals Q over some delta V, which I'll just write as V, right? Q over the voltage. So let's find an expression for charge. Let's try and find how much total charge is on the inside, right, in relation to the electric field that charge creates. So the easiest way is to use Gauss's law. So that means we need a Gaussian surface that symmetrically surrounds the charge configuration in question. So if we were to draw now a Gaussian cylinder of radius, we'll call r, we can write Gauss's law like such, closed integral of E dot dA. And so now the radius of our Gaussian cylinder is r. We want to find the area that is around that central charged cylindrical pipe plate thing. Okay, so let's see. Epsilon naught. The electric field here, is that constant for changing R, right? Is the electric field the same just above the central cylindrical plate as it is further away? No, it's not, right? The electric field drops off. So now we can't necessarily solve for a charge to put into the capacitance. Well, we have to use Gauss's law to find the electric field. So let's go back and rearrange this now. Well, not yet, I guess. So this is still Q, epsilon naught. Let's see. Electric field, I'm just going to leave it as E. And the dA, well, what's the closed integral of the area for the Gaussian cylindrical shell? Let's do 2 pi r, which is the circumference, right, times the length, which I haven't actually specified, of length L. Okay, so this is not necessarily a closed Gaussian cylinder. It's just a shell or surface. So our closed integral dA is 2 pi r times L. And the angle in between E and dA, oh, I haven't actually drawn a dA vector. For our Gaussian surface, the dA can point radially outwards. So that's in the same direction as the electric field, so thus cosine is 0. And now we can get an expression for E. Q over 2 pi epsilon naught r times L. Okay, hold that in your back pocket for a couple seconds, okay? Now we need to focus on the denominator in the capacitance equation, the voltage. How do we get the voltage between the central cylindrical plate and the outer cylindrical plate? Well, voltage is negative integral from initial to final paths or positions of E dot ds, right? And again, that minus sign right here, we don't really like that minus sign being in here because we don't necessarily want a minus sign in the capacitance. And that's okay. We are free to choose the path length, right? Well, not necessarily the path length. We're free to choose the direction, rather. In other words, we can go from the center outwards, or we can go from the outer, oh, gosh darn it, we can go from the outer inwards. There you go. So, if I were to say that if we went from out, let's do it again, out, in, that is our ds. If I were to say that ds is equal to minus dr, would that make sense? Right? The radial direction is directed radially outward. In other words, inside out. So if we go outside in, like I've shown here, well, that's a negative of that. So let's change this now to a negative integral from, well, let's just write this as from B to A, right, of E dot dr. So now we're changing our general path length from S to R, because R is the only direction that we're traveling in this path, the radial direction. So now, whoops, I forgot that it's a negative dr. There. Now the negatives cancel out, and we have integral B to A of E dot dr. Right? And it's positive. Okay, so let's see now. What do we have? Well, the electric field we have from Gauss's law above. So integral BA of all that, we have Q over 2 pi epsilon naught R times L times the, well, magnitude of dr, which is just dr, and then cosine of the angle in between E and dr. Oh, interesting. Now, since our ds is really dr, now E is outwards and our ds is actually inwards in the negative dr direction. All right, so now it turns out that this is cosine of 180. So our negative sign effectively comes back to bite us, right? But that's okay. That's okay. We'll see it goes away in a second anyway. All right, so the constants come out of the integral. Q over 2 pi epsilon naught. The length overall it is a constant, so that comes out. And so we just have a fairly straightforward integral of, whoops, of 1 over r, right? And so this gives us the following. Q 2 pi epsilon naught L times the natural log of A minus the natural log of B, right? Oh, should have a minus sign out front. And I don't like a minus sign out front if I don't have to. So we can rearrange those natural logs to do 2 pi epsilon L times natural log, right? I can flip the terms. Flipping the terms takes away the negative sign, and then I'm going to combine it in fractional form, giving me this. So that is the expression for the potential in between these two cylindrical plates. Now let's take this expression and plug it in for our capacitance, and this is what we get. We have our ordinary charge Q divided by what we just found. Q over 2 pi epsilon naught L times the natural log. So now we see the Q's cancel, and we're left with 2 pi epsilon naught L divided by natural log of B over A. And this is the expression for the capacitance for a cylindrical capacitor. Now notice, if we increase the length of this capacitor, right? If we increase the length, it gets longer, there's more room for these charges to be stored. So the capacitance increases. They're directly proportional. The spacing in between the plates. Well, if we decrease that spacing, right? So if this central plate A has a bigger radius, the separation in between the two decreases. Well, that's effectively taking the value for A and approaching the value of B. If A equals B, that's log of, say, 1. Log of 1 is 0. So in other words, as A approaches B, the log value decreases and the capacitance increases, which should make sense as well, because if the plates get closer together, it is easier to release the charge, right? The electric field is stronger and the potential is stronger. Okay, so that agrees with intuition as well. So this is how you calculate the capacitance for a cylindrical capacitor.